Today we're going to be talking about the big 5 kinematic equations. These are used in math, science, and real life. In math, they're used for parametric equations and also projectile motion. In science, they're also used for projectile motion and also kinematics. And then in real life, they might actually save you if you're in the middle or you're part of a kinematic or projectile motion. So let's just start with listing out the 5 equations, and we're going to derive them. So we have delta x is equal to 1/2 times vi plus vf. So vi plus vf times t. The second equation here is going to be vf is equal to vi plus at. Then the third equation is going to be delta x is equal to vit plus 1/2 at squared. The fourth equation is going to be delta x is equal to vft minus 1/2 at squared. The fifth equation is going to be vf squared is equal to vi squared plus 2 delta x a. So we have our 5 equations, and the reason we have 5 equations is because we have 5 variables. We have 5 variables, and every equation we only use 4 variables. So in the first equation, a is missing. In the second equation, delta x is missing. In the third equation, we don't have vf. In the fourth equation, we lack vi. In the fifth equation, t is missing. So these 5 variables make up the 5 kinematic equations. So it's important to understand what these stand for before we start to derive and understand the 5 equations. So a is going to be acceleration, and acceleration is basically the rate of change in velocity. So how fast my velocity changes, and velocity is basically speed with direction. So speed is 5 meters per second. Velocity is 5 meters per second to the east, or to the north, or to the south, or to this x direction. So acceleration is how fast my velocity changes, because I'm not going to be walking at a really constant and non-changing speed for the whole time of my journey, right? And the same thing, in the middle of motion, the object is not going to have the same velocity for the whole time. So we have acceleration, which tells us how fast our velocity changes. Say I had a football and I kicked it. So at first my vi, so let's just not talk about vi. I haven't talked about that yet. So our initial velocity, our starting velocity, is 0 meters per second, right? We start at 0 meters per second, and then someone kicks it, or maybe they roll it, so they apply force to this football, and then someone applies force to this football, and then it rolls, so after 5 seconds later, it has a velocity of, let's say, 10 meters per second. So that was a huge kick, I'm assuming. So it has 10 meters per second velocity now after 5 seconds. And we want to know, in these 5 seconds, how fast did my velocity increase? Because it obviously did increase. It increased from 0 to 10. So how fast did it increase? How many meters per second did it increase every second? Well, the answer is 2, right? If you think about it, 10 over 5 is going to be 2. So you go from 0 to 4, 6, 8, 10. That's how you increase, or that's how you think it would increase. It's actually the average acceleration here. So it's the acceleration in this instant for 5 seconds as a time interval. So our acceleration would be, a is going to be equal to 2 meters per second squared for this situation. And the reason we have that is meters per second squared thing is because it's basically we increase 2 meters per second every second. So now we understand acceleration. Let's look at delta x. So delta x is, delta is just change in. So delta displacement is just going to be change in displacement. So delta represents change in, and x is what we use to represent displacement. So what is displacement though? Well, displacement is basically the change in position of an object. So say my football started here and it rolled all the way across here, and that distance here is 10 meters. My displacement, delta x, would be 10 meters because that's my change in position. My football over here is 10 meters away from its original position, right? However, if my football rolled like that, say there was a side kick there, and it rolled for, let's say, 20 meters. So which one's my displacement now? Is it 10 meters or 20 meters? It's still 10 meters because my football ended up in this position, and this position here is still 10 meters away from my original position. The 20 meters here of my path is the distance. The distance is basically the area or of ground that my object covers when moving. The displacement is the distance of my object from its original position. The delta x is going to be the change in displacement. Vf is the final velocity. So the velocity that I end with, so just now for the football, after 5 seconds, I end with a 10 meter per second velocity, right? So that's my final velocity. That's Vf. So initial velocity in this case is going to be, so Vi is initial velocity. And initial means the thing we start with. So initial velocity is the velocity you start with. So you start with 0 meters per second, right? So that's your Vi, because when you started this motion, the football wasn't even moving. No one was kicking it, and it stays not moving. So the Vi is 0 meters per second here. So t here is a time interval. Time interval is a change in time in this motion. So how long would it take this motion to be accomplished, this projectile motion or whatever motion this is? How much time do we have for Vi to become from 0 to 10? How long time did we have for the football to travel 10 meters? Well, we had 5 seconds, right? So I know that doesn't make sense, but okay, we have 5 seconds. Okay, let's just say this is 50 meters. Or actually, you can say it's 10 meters. So we have 5 seconds to travel 10 meters, right? So that's our time interval. There, t is going to be 5 seconds. We have 5 seconds to accomplish this motion of letting delta x be 10 meters. So these are our 5 variables, and I hope you understand those. So if you don't understand those, I encourage you to pause the video and think about this on your own. So draw a few graphs. You can also copy this down and also, search up the definitions. So now, assuming you understand these variables, we're going to derive them. So let's just come up with an example to help you understand how do we derive the formulas. So you can obviously use some clever algebraic manipulation, but we're not going to do that now. So we're going to use the most logical way. So firstly, we're going to draw a velocity time graph. So a velocity time graph compares velocity to time. We have velocity for the y-axis, and we have time for the x-axis. So velocity is meters per second in this case. So our standard unit is meters per second for velocity, and our time here, sorry, that's not x, that's t. So our time is going to be seconds for standard units, right? So what does this do? It basically tells you at this specific time interval, what is my velocity? So let's say I have this line here that shows my change in velocity compared to time. This basically says my velocity is increasing over time. I don't know what's my velocity at the specific time interval, so I just find this point on this line, and I know my velocity. So that's the use of this graph. And you can also use it to calculate acceleration, because acceleration is just how fast my velocity changes over time, right? So let's just come up with an example. Let's say I started with a velocity of 5 meters per second. So let me just draw this 5 meters a bit upwards. 5 meters per second, right? And then, so that's my origin. I started with a velocity of 5 meters per second. Vi is going to be 5 meters per second. And then after 3 seconds, so let's say my motion is only lasting for 3 seconds. I don't care whatever happens after 3 seconds. So after 3 seconds, let's say at 3 seconds sharp, my motion is going to be 11 meters. My velocity is 11 meters per second. So I have this point over here on my graph. That corresponds to at t equals 3, v equals 11. And at this point here, it corresponds to when t equals 0, I have v equals 5. So vf here is going to be 11 meters per second. My time is going to be 3 seconds because I had 3 seconds to do this motion thing. So now we just want a and delta x. So we're going to derive a formula based on the calculations of a and delta x. So firstly, let's just connect this. So we know that this is approximately what it looks like for our velocity and time graph, because the velocity increases as our time passes on, so that it starts from 5 and it reaches 11. So acceleration is, we want to know how fast did this increasing thing go. So the process here, so we want to know, how fast did my y coordinates change, because y is velocity, right? So how fast did my y coordinates change? Well, that is just the steepness, gradient, or slope. So it's just the gradient of this. So that's just the gradient of this line here, because we want to know how steep is this. So how fast did it take for my y value to increase from 5 to 11? That's just the gradient. So now I also want to know my delta x. So what's delta x? This is the hard part that you have to understand logically, and I struggled for a lot to understand this one. So I hope you understand this after I explain it. So delta x is just the area here, and why is that? So the area here basically says, let's just imagine that I have a lot of tiny time intervals, right? So I have infinity many time intervals here, between 0 and 3 seconds. I have a lot of time intervals. You can't count them. There's infinity many. And for every time interval, we have a different velocity, right? We have a different velocity, and for every time interval, so that's because the time intervals are infinitely small, then every time interval, my velocity is going to be, my displacement, my delta x, my change in time interval is going to be velocity times time, right? So velocity is going to be the specific y coordinate, and time is going to be the specific x coordinate, because my time interval is infinitely small. So I don't have to care about how much exactly how the velocity actually is, how it actually works. We only have to care about this tiny coordinate here, because it's infinitely small. So we can just call this a tiny fraction of the time. And you know that in this point, let's say you add coordinates TV, then you know that in this case, during this time interval here that's infinitely small, your delta x is going to be v times t, right? Velocity times time. Same thing for in primary school, you learn that distance is equal to speed times time. So if you just have all these tiny intervals together and you add them up, then you get this whole, if you add them up, then you get this whole time, you get the total distance that you've traveled, the displacement you have traveled. So if you add all the tiny, infinitely small time intervals and the change in displacement in these infinitely small time intervals, then you get the change in displacement for the total time interval, 3 seconds. And what is the sum of all of these infinitely small change in displacements? Well, it's basically this whole graph here, because every single dot here between the time interval corresponds to a specific velocity, which also corresponds to a specific displacement. If you add these changes in displacement up, then you get this whole graph, right? You get every single line here counts in, and there are infinitely many lines, so this just gives you the whole graph here. So basically our delta x is the area of the trapezoid, or trapezium, but okay, I'll just call it trapezoid. So the area of the trapezoid.